In this section, we're going to talk about area. Area and indefinite integrals and definite integrals have a very close relationship. We're going to talk about just area under the curve. We're going to introduce how it has to do with the integral in the next section. Before we start talking about area, we need to introduce something probably new, and that is sigma notation, when we're talking about summing a bunch of terms up. So sigma notation refers to the Greek letter sigma, which is this thing right here, this sigma. And just some terms right here. So this sigma, we have I in there is called the index. The a sub I is called the ith term of the index. The lower bound of this sum is 1, and the upper bound is n. And what this means, sigma refers to summing a bunch of terms up. So we have this sigma of a sub I from I 1 to n. We're going to plug in all the values from 1 all the way up to n into that a sub I, and we're going to add them all up. So we have a sub 1 plus a sub 2 plus, here's a little typo, that should read a sub 3 plus a bunch of things all the way to a sub n. So let's look at some examples. We're actually going to skip the first example right now because that's actually a little bit difficult because it's pretty easy. We'll see what I mean by that in a second. When we talk about this part B, we have the sum from I equals 3 to 6, I plus 4. So what this says is that we are going to add up all the terms starting at 3 going all the way up to 6. So the first one is 3. So we're going to plug that into I plus 4, giving us 3 plus 4. Then we're going to do the same thing for plugging in 4. We're going to do that all the way up to 6. So you have 3 plus 4, 4 plus 4, 5 plus 4, 6 plus 4. This first term is from the I equals 3. Second term, I equals 4. Here's I equals 5. Here's I equals 6. So if you would add that all up, that would be 7 plus 8 plus 9 plus 10. Which would give us, a grand total of 34, if I'm not mistaken. All right, so that's just a nice way of writing this complicated sum. We could also take that, we're going to redo this here in just a second. Instead of thinking about I plus 4, we could think about this as the sum from I equals 3 to 6 of I plus the sum from I equals 3 to 6 of 4. So in that case, we'd actually have two sums there. We would have, plugging in an I, 3 plus 4 plus 5 plus 6. And then here, this goes to our first example too. There's nothing to plug in for I, so then we're just going to be plugging in. We're just going to have 4 each time. So again, this is representative of I equals 3. Here's I equals 4. I equals 5. I equals 6. Then the same thing here. I equals 3, 4, 5, 6. Different way of thinking about it, you can break a sum over addition. That's rules from first, second grade kind of idea that addition is commutative. All right, we're going to erase some of this so we can keep on working. So going back to that first example, there is no I in that term. That doesn't stop us from adding things up. It's just that for each term, it's going to be a 3. So we're going to have when I equals 1 all the way up to 7. So this would be a 3 and a 3, and it's going to be a 3 for every single term. And actually, we could just write this as, since we have 7 terms, 7 times 3, or 21. All right, let's get to some more complicated sums real quick. So in example C, we have k instead of I. That doesn't make a difference. You can call that any variable you want. The reason we call it I is just because index starts with the letter I, but it could be anything. And here we have from 0 to 4. So the first thing we're going to plug in is 0. I should say k equals 0. We're going to have k equals 1, k equals 2, k equals 3, and k equals 4. And we plug that in, we'd have 0 plus 1 squared over 0 plus 3 plus 1 plus 1 squared over 1 plus 3 plus 2 plus 1 squared over 2 plus 3 plus 3 plus 1 squared over 3 plus 3 plus 4 plus 1 squared over 4 plus 3. And we could simplify that with some basic rules. We would get a value out. Looking at another example, probably a little more difficult because it's more abstract. Here we don't have specific values we're going to have. We have this f of x sub I. So it's going to refer to different x values here, but this would be f of x sub 1 times delta x. Delta x is some constant, plus f of x sub 2 times delta x. And then we stop at f of x sub 3 times delta x. We start at 1, we end at 3, do everything in between. And in this case, this is some abstract sum, but this is what we're going to be dealing with in this section and future sections when we talk about summations. This sigma notation, this idea of summations, is very important the further you get on in math. In Calc 2, you will deal with this notation a whole lot, talking about infinite sums instead of just finite sums like we have here. All right, now let's bring this back to area, and we'll see where the sigma notation comes in a little bit later. So, first question has nothing to do with calculus at all, is find the area under the curve negative x plus 4 on the interval 0 to 3. So it might help to start by just graphing this function and seeing what comes out. So we're going to be thinking about just the interval 0 to 3. So let's think about our function there. We're going to do the x value 0 to 3. We're going to graph the function negative x plus 4. That has a y-intercept of 4 and a slope of negative 1. It's going to go through these 2 points. There's our function. And when we're talking about find the area under the curve, that means that we are looking for this area right here, all the way up to the 3, not including that little triangle at the end. So if I want to find this area, all I need to do is look at common area formulas. So I know that. So we have that the area of a triangle is 1/2 base times height. So we could think about this area as the area of this big triangle minus the area of this little triangle at the end. And that would give us our area that we're looking for. So the area of the big triangle is going to have 1/2, the base is going to be 4, and the height is going to be 4. And this will give us an area of 8. And the little triangle, not the yellow stuff, just the red stuff, has a base of 1 and a height of 1. So this will be an area of 1/2 1 times 1. One half. We are subtracting those values, so we have total an area of 8 minus 1/2, that is 16 halves minus 1/2, or 15 halves. And since we're talking about area, we should talk about units squared here. All right, so to find this area under the curve, under this function, we are just looking at simple area formulas, in this case the area of a triangle. Let's go to a more complicated example. Here we have find the area under the curve f of x equals x squared on the intervals 0 to 2. And we'll start in the same way. Just draw a picture of this function and see what happens. We're going from 0 to 2. And when we graph that function, we have the point 1, 1. We have the point 2, 4. And we have this function right here. It's going to look like a parabola. We are looking for the area under the curve. That's going to be this area right here. So this is a pretty simple function. It's one that we're very used to and we've seen a whole lot. But to find that area is a much more complicated question than the one before. In fact, there is no nice formula that we have to find that area. We don't have straight lines, and that makes it very difficult. So you could think about how can you find this area, and that's a very good question to ask, and it's worth brainstorming a little bit about. But there's really no nice way without some kind of calculus ideas behind it to find that area. So we're just going to write that this is not an easy area to find. Because we don't have straight lines. Or maybe circular lines would be nice as well, but these are not. Okay, we don't have a nice formula to do that. So when we're dealing with this, the best that we're going to be able to do at this point, without some extra things we're going to learn in later sections, is that we are just going to have to estimate this area. Okay, this is a very difficult problem for us. The best we can do is estimate, and what we're going to use to estimate is rectangles. Now going back to the picture, there are other ways that we could estimate this. We could estimate this area with a triangle. Maybe we could estimate this area with a couple triangles. That actually looks pretty good. Or not triangles, but maybe some trapezoids. But we're going to use rectangles because rectangles are nice and easy shapes to find the area of. So looking at this again, we are going to use rectangles to estimate this area. So we're going to look at something like this. Maybe use 2 rectangles to estimate that area. We could use maybe even more. And we're not saying we're finding the area exactly, we are just estimating. So we're going to do this with a different function here. We're going to look at the function 4 minus x squared on the interval -1 to 3. And again, it might help to draw this function to see what we're trying to do. So we have -1 all the way to 3. We're looking at 4 minus x squared. So when I do 4 minus -1 squared, that's going to give me a 3. When I plug in 0, that's going to give me 4. When I plug in 1, that's going to give me a 3. When I plug in 2, that's going to give me a 0. And actually, at this point, I just want to go -1 to 2. We're going to deal with stuff below the x-axis in the next example. So this function is just going to be from -1 to 2. we have that function right there. And we're trying to find the area under that function. Again, we are looking at this area right here. It's easy to graph, but it's not necessarily easy to find what that area is going to be. So we have this. We're going to estimate, we're going to approximate this area with rectangles. And there's a number of ways that we can do this. Just for the time being, in this example, we're going to do this. We're going to estimate with 3 rectangles. Okay. The base of those rectangles are all going to be the same. And they're going to lay on the x-axis. But the height of those rectangles is going to change. Depending on what x values we are talking about. So, looking at this again, go to a new page here. We're looking at from -1 to 2. And we're going to deal with 3 rectangles. If the base is all the same, then the base of the rectangle should be equal to the length of that interval. This would be a 2 now. The length of the interval divided by the number of rectangles. In that case, that's going to be a 3 divided by 3, so we're looking at a base of 1. So we can actually draw the base in all of those rectangles. Okay, what's going to change is the height of those rectangles. Draw our function again real quick just to sketch it. Okay, we know that the rectangle is going to depend on the function value at some point. Let's just take a look at that first rectangle here. From -1 to 0. For that rectangle, I need to determine a height of that rectangle. So again, the height of the rectangle is determined by the function value. I should say not by the function value, but by a function value on the interval of the base. So there are some options there, right? So for the first rectangle, Some options may include that we could use x equals -1. Let's actually draw these rectangles in here. We could use x equals -1 as our height, and we would go up to -1 on the function, and that would correspond to the height of our rectangle. Right, so the height would be f of -1, in this case 4 minus -1 squared, or 3. We could also choose x equals 0, as that's on that interval as well. We would go up to 0 on the function and draw a rectangle down from there. In this case, the height would be equal to f of 0, or 4 minus 0 squared, 4. And there's more options than that we could choose. We could look at another common one. Could be, how about x equals -1/2, halfway in between those values. And we could go up to the function value at -1/2. We could draw a rectangle there as well. In this case, the height would be f of -1/2, 4 minus -1/2 squared. That would be 4 minus 1/4, or 15/4. And there are a lot of other options that we could use. Anything in between -1 and 0 could be a height that we could consider. We're going to stick with just these three options. These are kind of nice options. Either the very left endpoint, the right endpoint, or the middle point in that interval. And that's going to give us 3 of our 5 kind of different ways to deal with this area. So we're going to do that for each rectangle. Let's just think about, for the second rectangle here, we could maybe choose the right endpoint. And then maybe for the last one, we could choose the middle point. Giving us our rectangles. We're trying to find the area of those rectangles. So, moving on, let's talk about the different ways to calculate this area. We're going to have 5 different rules. First one we're going to look at is the right endpoints. And as it says, we are going to use the right endpoint for each subinterval, for each subinterval. Let's draw a picture of that. So from -1 to 2, we have 3 different intervals to consider. We have from -1 to 0, 0 to 1, 1 to 2. And we are going to use the right endpoint in each of those intervals to find the height of the rectangle. So for the first interval, we're going to use the right endpoint, that's 0. Go up to where the function is 0, we can draw a rectangle there. We're finding the area of that rectangle. For the second one, we're going to use the right endpoint, that's going to be the 1. Draw the rectangle there. And for 2, we're going to use the right endpoint, that's just 2. That's a very stupid rectangle. It has a height of 0, but that's what we're going to deal with. So here, the area is going to be estimated by the area of the three rectangles. So that is going to be base times height of each of those. So we're going to look at the first rectangle, second rectangle, third rectangle, and we have base times height of all of these rectangles, and we are going to add them all up. We said on the first page that the base of these rectangles are all 1. And the height of these rectangles depends on that right endpoint. So the first one is going to be f of 0, which we know is 4. The next one's going to be f of 1. And this corresponds to the right endpoints of these subintervals. The last one's going to be f of 2. We're going to take those values and add them up. Now note what I have here is I could actually write this as a sum using our sigma notation. This would be the sum of 1 times f of I from I equals 0 to 2 would be another way to write that sum. In this case, this would give us 1 times anything is just the anything, so this is going to give us a 4 plus 3 plus 0 would give us a 7 units squared. So let's talk about this in general. We have if we have n rectangles, we could use as many as we want, then the base is going to be called delta x. It's the change in our x value, and that is going to be b minus a divided by n. That's the length of the interval divided by the number of rectangles that I have. B minus a divided by n. And the height of the rectangle is going to be the function value. So for the right endpoints, or the right endpoint rule, or the right rule, we are going to have the sum from I equals 1 to n of f of x sub I times delta x. In this case, x sub I is the right endpoint. So in our example here with n equals 3 rectangles, this would be x sub 1, this would be x sub 2, this would be x sub 3. All right, this would be the right endpoint, and this would approximate the area. All right, we are going to do this 4 more times. We're going to do it in less detail as we go on, but we're going to have, instead of the right endpoints, we could use the left endpoints. We could use the middle point, the midpoint, instead of those two. And also we could have a rule where we're always going to pick the lower function value or the upper function value. And we'll see what we mean by that as we get to it. All right, we're going to redo this example now with left endpoints. So we'll redraw the function. We're going from -1 to 2. And we'll draw this function again. All right, so if we're using the left endpoints and we still have 3 rectangles, we're going to say n is equal to 3. That's the number of rectangles. Our 3 endpoints are going to correspond to the -1, the 0, and the 1. We can think about drawing the rectangles at those 3 points. Then it's just a matter of finding the area of those rectangles. So, area is going to be approximated by, we'll use this sigma notation, sum from I equals 1 to 3 of f of x sub I times delta x. In this case, delta x is b minus a divided by n. That's the length of the interval divided by n. That's 1. We've kind of seen that before. And we're thinking about x sub I. We have x sub 1 is there, x sub 2 is there, x sub 3 is there. So this is going to be f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x. That's actually the exact same for the right endpoints. It's just that the x sub I represents different values. So in this case, this is going to be f of -1 times, said delta x, we'll write just 1, plus f of 0 times 1, plus f of 1 times 1, and that will give us 3 plus 4 plus 3 will be a 10 units squared. That is the left endpoint approximation of that area. Let's do it again. Let's do midpoint this time. And this time we're going to do it without drawing the picture. We're going to start from the beginning. So really all we need is the interval, the -1 to 2. And if I'm going to break that up into 3 different rectangles, I'm going to have a base of 1 in each point. And if I want to determine the midpoint of each of those, I just need to find the midpoint of each of those 3 subintervals. In that case, that's going to be -1/2, 1/2, and 3/2. So the area here is going to be, and we're going to do something a little bit different this time. How about, since delta x is a constant, we can actually bring that out in front of the sum. We could say something like this, or delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3, and we have this is equal to 1 times f of -1/2 plus f of 1/2 plus f of 3/2, which would be 1 times 4 minus -1/2 squared plus 4 minus 1/2 squared, whole thing, plus 4 minus 3/2 squared. That would be the midpoint rule, and that will correspond to a different picture. We have 2 more that we're going to look at. We could also look at the lower sum, and this is that we use the least function value on each subinterval. So in this case, we need to think about what are the function values. It might help to have the picture in this one. So for the least one, we're still going to use n equals 3 in this case. Our x values are going to correspond to, if we think about the interval from -1 to 0, the least function value is going to be at -1. So this is going to be my x sub 1. For the interval 0 to 1, on the interval 0 to 1, the least function value is going to be at 1 here, because that function is decreasing on that interval. So that's going to be our x sub 2. And we're going to have x sub 3 is going to be the 2 here, as that's going to be the smallest. Again, the function is decreasing on that interval. So for the lower sum, we are going to have delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3. And that's going to give us a 1 times f of -1 plus f of 1 plus f of 2, 4 minus -1 squared plus 4 minus 1 squared plus 4 minus 2 squared, or 3 plus 3 plus 0 is going to be 6 units squared. And this is guaranteed to be an underestimate of the actual area, because we're using the least function value on all those points. On the other hand, we could be doing the upper sum, and that is we're going to use the greatest function value on each subinterval. So in that case, for the first subinterval, we would have the 0 would be our x sub 1, because that's going to be the greatest function value. For the second interval, it's also going to be the 0. That's going to be our x sub 2. And for the third one, we're going to have x sub 2 is going to be the same as x sub 1, and here we're going to have x sub 3. So the upper sum here is going to be delta x, again, times f of 0 plus f of 0 plus f of 1. 1 times 4 plus 4 plus 3, which will give us 11 units squared. And this is guaranteed to be an overestimate of the actual area. So we could say that our area is bounded in between 11 and 6 units squared. It's always going to be trapped in between the lower sum and the upper sum. Looking back at the midpoint rule that we had, might be able to say that this might be a better estimate for the actual function, We could also say that our value maybe is trapped in between the left and the right endpoint rule as well. But this one, we definitely have the case for lower and upper sum. So we're going to do this again. We're going to use a different function now, x cubed plus 1, and we're actually going to change this. We're going to do just 2 rectangles to see a different value of delta x. And the difference in this function and the last one is we're going to have negative area to consider, and we'll talk about that just a second here. So let's draw this function first. We have x cubed plus 1 on the interval -2 to 2. This is going to look like the function x cubed moved up 1 unit. If we think about plugging in 0, that's going to give us a value of 1. We plug in 1 and -1, we're going to get values of 2 and 0. If we plug in 2, we're going to get a value of 9. And -2 is -2 cubed is -8 plus 1 to give us a -7. Connecting those dots, we have a nice curvy x cubed kind of function moved up 1 unit. Now we're talking about the area under the curve. It's easy to see for the positive part, we're going to have this area. But for the negative part, we're talking about the area from the function to the x-axis. And since this is below the x-axis, this is negative area. That's going to be something that we're going to have to consider in this problem. All right, let's think about what delta x is going to be in all of these problems. This is going to be b minus a divided by n. And if we're going to use 2 rectangles here, this is going to be the left endpoint 2 minus the right endpoint -2. It's the length of the interval divided by 2. That's 4 divided by 2, which is 2. That's going to be the base of each rectangle here. So when we are doing this, all we really need to consider is the interval itself, -2 to 2. And if I am going to divide that up into 2 different subintervals, I can just think about the interval from -2 to 0 and the interval from 0 to 2. This is the first subinterval, or the first rectangle, and this is the second rectangle. So from -2 to 0, we're going to be thinking about 5 different ways to add up or think about which endpoint, which value we're going to use. The left endpoint, the right endpoint, the middle point, the lower sum, and the upper sum. So let's think about each of those separately. We have, first, let's deal with the left endpoint. In this case, for each of those subintervals, we are going to use the left endpoint. That's going to be the -2 and the 0. So when we're calculating this area, we're going to have delta x times f of -2 plus f of 0. Delta x is 2 in this case. F of -2 will give us a -7, and f of 0 will give us a 1, and this will give us a 12 units squared. Let's think about the right endpoint. Notice on that last problem too, I guess I should say this, that the rectangle, if we would draw that in the picture, would be using that value from -2. This would be a rectangle that would be below the x-axis. From the x-axis down to that function value, and that would have a negative area, in this case an area of negative 7 times 2 and negative 14. And I drew that incorrect, so we have a delta x is negative 2. It would be that rectangle right there. All right, for the right endpoints, we're going to use the 0 and the positive 2. This is going to be delta x times f of 0 plus f of 2. This is going to give us 2 times 1 plus 9, or 20 units squared. Just depends on what the x value that you're looking at is. For the lower sum, this is actually going to be the same as the left endpoint, because f is increasing. So the left endpoint is always going to be the smallest function value. And for the right sum, or sorry, for the upper sum, this is going to be the same as the right endpoints. Again, because the function is increasing. So then we also have the midpoint rule. In this case, we're going to use the midpoint of each of those subintervals, -1 and 1. And this is going to give us a delta x times f of -1 plus f of 1, which will give us 2 times 0 plus 2 would be a 4. All right, in this case, we know that the actual area has to be in between the lower sum and the upper sum, 12 and 20. What that actual value is, we don't know. We're going to figure that out in the next section. We're just getting an approximation of that area. Note that because the function is increasing, that we could think about this instead of lower and upper, we could think about it as left and right. And if the function was decreasing, we could think about that in the same way, just backwards. The left endpoint would be the upper sum, and the right endpoint would be the lower sum. So the last question in this section is basically, we have an approximation of the area, but how can we get a better approximation of the area? And again, you should pause the video and you should think about, how can you get a better approximation of the area? And there's a number of ways that you can do it. Some ways that we're going to think about is, we could use a different shape instead of rectangles. So for instance, if you have some curvy function here, you could approximate the area instead of with rectangles, but with some trapezoids, or kind of like triangles on top of rectangles. And you'll talk about in a Calc 2 course the trapezoid rule instead of some of the other rectangle rules. And there's a lot of different things you could do instead of that. We're not going to deal with it in this course. The biggest thing we're going to think about is we could use more rectangles. So let's think about a couple different examples here, or just one example in a different way. We're going to think about the same function we're going to think about this on the interval a to b. And we're going to think about what can we do if we have different number of rectangles. So if I had, say, 3 rectangles, and I use the, looks like I'm drawing the left endpoint rule, so it'd be n equals 3. That might be a pretty good approximation, but there's still some gaps in between the rectangles and the function. If I use instead more rectangles here, so here I used n equals 7, the gaps in between the rectangles and the function is harder to see, and 3 and 7 are both very, very small values. What if I used a lot of rectangles, and there seems to be no difference in between the function and the rectangles themselves when I have this many. Okay. And note that this is what, maybe like 15 or 20 rectangles that I drew. That is not a very small number. What if I had 100 rectangles or 1,000 rectangles or 1,000,000,000 rectangles? The area inside the rectangles would be almost exactly the area under the curve. So the more rectangles you have, the better approximation. And this is getting to our really big calculus concept. Really nothing we've done so far has anything to do with calculus at all until this next part, which is as the number of rectangles gets larger, as n goes to infinity, we have that the area is actually equal to adding up the area of the rectangles, which is given by this. This is the area of the n rectangles. And instead of thinking about just value of n, if we let n get bigger and bigger, this is not just approximately equal. So as n goes to infinity, the approximation changes to an equal sign. And that is the whole point of this calculus concept. We've seen this a few times already in this course, that you can approximate kind of what's going on with a finite number of value of things. Once you attach that limit onto it, it now becomes equal to what we're actually dealing with. We saw this with derivatives earlier on. We talked about the slope of the secant line. This is about the value of the derivative. But if you actually attach a limit onto that, in this case, if you let delta x go to 0, then this actually becomes equal to the value of the derivative. And that's what happens in all of calculus, is that you think about a finite number of things that's approximately equal, attach the limit, it becomes equal to. We're going to see in the next section that instead of area, we're going to talk about the definite integral, which is a little bit different than the indefinite integral, to find that area.